Alright, so we're going to continue our discussion of free fall from rest like the previous example. Essentially, he's just walking off so he doesn't have an initial velocity, or if we're dropping something. Just recall the equation delta x equals vit plus 1 half at squared. If we're considering an object falling from rest, the object is going to have an initial velocity of 0. So that vit term cancels out. We also know that the acceleration is g, the acceleration of gravity. So let's replace that a with a g. Finally, delta x, since we're talking about the distance that it's falling, we already know that it's probably falling to the ground. So we're going to call that position 0. Anytime we're taking that height that it's falling minus 0 is going to be equal to the final position x. So we'll just call it simply x. And if something's free falling from rest, we know that it's a function x equals 1 half gt squared. We also know that the final velocity is equal to the initial velocity plus at, again acceleration being g. So since initial velocity is 0, our velocity at a certain time is v equals gt. So let's try to find velocity if we don't know the time, but rather if we know the position. So what's velocity in free fall as a function of a certain position? We know that, again, v equals gt. So let's go ahead and solve this to get t by itself so we have it in terms of x. We know that 2x equals gt squared. Then let's divide g on both sides. So we get 2x over g equals t squared. So t is going to be the square root of 2x over g. So if we put this t into here, velocity is simply g times the square root of 2x over g. We could also write that as g times 2x over g to the 1 half power. Since there's a g to the first power on top and a g to the 1 half power on the bottom, that would be g to the 1 half power times 2x to the 1 half power. So this whole thing is under the radical, under the square root sign. So we know as a function of x, v is equal to 2 times g times x to the half power, or the square root of 2gx. So just looking at a strobe diagram again, taking a picture of a ball falling at each second falling from rest. Notice that the position is increasing a lot each time. We go from 4 to 20 roughly to 44 to 79. It's increasing a squared amount, whereas on the green numbers, the velocity is only increasing linearly. You're only adding 9.8 meters per second on each second. So notice how the position changes a lot more. That's why that function turns out the way it did. So go ahead and answer this concept check on the back of your video summary sheet. You drop a rock from a bridge to the river below. When the rock has fallen 4 meters, you drop a second rock. As the rocks continue their free fall, does their separation increase, decrease, or stay the same? Go ahead and answer that on your sheet, and we'll discuss it in class tomorrow. So looking at another example, now we have something that's shot up at a certain speed and it comes back down to the ground. So a volcano shoots out blobs of molten lava called lava bombs from ground level. A geologist observing the eruption uses a stopwatch to time the flight of a particular lava bomb that is projected straight upward. if the time for it to rise and fall back to the ground is 4.75 seconds, and its acceleration is 9.81 meters per second squared downward, what is its initial speed? In this case, what I would do is I would think of this as two separate problems. But before we even do that, we want to make sure we have a diagram and we label which direction is positive. In this case, I'm actually going to call up positive. Since we're dealing with motion in both up and down directions, let's just call up positive, meaning we're going to use negative 9.81 for our acceleration the entire time throughout this problem. Our time it takes to go up and down is 4.75 seconds. And again, we're trying to find the initial speed VI. So what I would do, I would consider this as two separate problems. There's the part where it's going up. There's the part where it's coming back down. On the way up, we know its final velocity is going to be 0. It's going to go up, up, up until it stops. It's going to end up with a final velocity of 0. The time it's in travel up is going to be the same as the time in travel as it comes down, right? So half the time it's going to go up, half the time it's going to come down. So let's take 4.75 divided by 2. We know that the time is going to be 2.375 seconds on the way up. It's also going to be that on the way down. So now we have a VI, an A VF, and a T. We don't have more than one variable that's unknown. So let's use our equation VF equals VI plus AT. 0 is going to be equal to our initial velocity plus negative 9.81 times 2.38 seconds. We'll keep our sig figs consistent there. So we should get 0 is equal to VI minus 23.3. And if we throw this on the other side, we should find that our initial velocity equals 23.3 meters per second. So go ahead and try this on your own. Again, you're going to want to pause this because I'm going to show the answer shortly. Try this on the back of your paper. A second lava bomb is projected straight upward with an initial speed of 25 meters per second. How long is it in the air? The answer for this should be not negative 23.3 meters per second. The answer to that should actually be 5.1 seconds, because we're asking how long. So please ignore my answer there. I made a mistake in the PowerPoint. It should be 5.1 seconds. Notice here that the lava actually lands at the same speed at which it was launched. We're going to talk about that on the next slide. When something is launched upward, the time going up, again, is going to be equal to the time coming down, as long as there's no different elevation happening. If you're standing at the same elevation, you launch it up, it comes back down, the time going up will equal the time coming down. As you can see, as it goes up to the top, 3 seconds up and 3 seconds down. Also, the velocity of the object as it reaches its highest point, that highest point occurs halfway between. Notice the slope at the top, the tangent line, is going to be 0. It's not going to have a slope. That's telling me that my velocity is 0. So remember, the velocity is the slope of a position time graph. Finally, the launching speed, if you notice, if I can draw a slope of the tangent line here, it's about the same slope as the tangent line for the landing speed, only they're in opposite directions. One has a negative slope, 1 has a positive slope. Sorry for my sloppy slope lines here, but as you can kind of see, going sort of up at an angle to the right on the left side, up at an angle to the left on the landing side. So at this point, if you'd like, you can read the ball thrown upward section on pages 72 and 73. Let's go ahead and continue looking at acceleration in terms of graphing. Notice that how the time dependence of position, velocity, and acceleration in these three graphs. On these three graphs, we're using that dotted line to represent our midpoint. So as you notice, this is our position time graph. It goes up to where it hits its highest point in the middle, and it comes back down. Notice the parabolic shape being that distance is increasing as a squared function of time. If we look at the velocity, remember the velocity is the slope of our position time curve at any point. The slope of this position time curve as we go along is decreasing until it hits 0. And then it still continues to decrease as we go to the negative side. That's why we have a continually decreasing velocity time graph. Notice right here at the midpoint, our velocity again is 0, just like it was over here. Because we have a continually decreasing velocity till it hits 0. Then as it's going up, slowing down, slowing down, slowing down, when it comes back down, it's speeding up, speeding up, speeding up. But the velocity is still decreasing. So the speed is getting more and more negative, but the velocity is decreasing. So that's why we have a constant slope, a line, because our acceleration, as you see, is a constant negative 9.8. So this slope of our velocity time graph should be negative 9.8, the value of our constant acceleration line. Notice the middle of that doesn't really matter. It just happens halfway through the time because of no matter where I am in free fall, my acceleration is negative 9.8. So let's look at an example here. A hot air balloon is rising straight upward with a constant speed of 6.5 meters per second. When the basket of the balloon is 20 meters above the ground, a bag of sand is tied to the basket comes loose. How long is the bag of sand in the air before it hits the ground? So we want to know the time that bag of sand is in the air. We know that the basket is 20 meters above the ground when it's launched. So we know that its initial, or its let's see, its initial speed is 6.5 meters per second because it's going 6.5 meters per second upward. We also know that its initial height is going to be 20 meters. I would suggest using our equation. We have an x, so we'd use delta x equals VIT because we have a VI. We're trying to find T. We also know, again, A. Let's call the up direction positive. So let's call A negative. 9.81 meters per second squared. So let's take this picture off for a sec. So if we substitute our numbers in here, let's put x final. We know the final position. We want to know before it hits the ground. So let's say 0 minus 20 equals Our initial velocity we know is